Okay, I left you with this little problem to think about. We've got a cluster of stars over here. So here's the cluster. Here's us over here viewing this cluster from some distance d away. And at the physical dimension of the cluster, I'm just going to call L here. So you've got some length L. And if it's reasonably spherical, then obviously the distance this way should be the same as the distance this way. So we can estimate this L here from the information on the angular diameter. So we were told that the cluster subtended an angle of about 1 degree on the sky and was a distance of 1,000 parsecs away. So if we just keep all the distances in parsecs here for a change, since we don't need to, we calculate theta in radians. So this is this formula. L is just theta times d. This is the small angle approximation. So this just comes from the definition of radians themselves. So if you go back to just the definition of radian, if this was a little arc here, okay, then the length of that arc would be theta in radians times the radius of the circle, which is the distance d in this case. So that's where this formula comes from. Okay. So we just need to work out theta in radians. So I just did this by firstly converting it to arc seconds. So 1 degree, basically times 60 to give you 3,600 arc seconds, and then divide by this magic number, which is the number of arc seconds in a radian that we worked out in workshop 1. Okay. So 206,265 is a number that's always imprinted on most astronomers' brains. So that is theta in radians. So if we want to know what L is in parsecs, then we can just times theta in radians by the distance d in parsecs to give us that L in parsecs as well. If you want to, you can convert everything to meters and convert it back again, but this is a bit quicker. So that means that this would be 17 parsecs across, okay, and also 17 parsecs this way. Okay. So if you think about that now as a sort of percentage error on the distance, if you like, so there's a spread of, say, roughly 20 parsecs across here on a total distance of 1,000. Okay, that's basically a 2% error in the distance going back into that absolute magnitude formula that we talked about earlier. Okay, so 2% for astrophysics is neither here nor there. I mean that's already pretty accurate, more accurate than a lot of other uncertainties that we would normally have to deal with. So therefore, you can begin to see that approximation of assuming all the stars are actually at the same distance is a pretty good one. So that allows us to sort of unlock the power of these color magnitude diagrams that we've been discussing. Okay, so let's get a little bit more detail on star clusters themselves now. And for the purposes of this module, we can just divide them into sort of 2 very common types of cluster. So these are referred to as open clusters, and the other type is globular clusters. Okay. So let's discuss each of those in turn. So open clusters, these are typically maybe have anything from 100 to 1,000, maybe even more members. So by members we mean stars here, of course. So it's a cluster of order of 1,000 stars on the sky. The one behind me on the background here is a typical open cluster. Okay. And perhaps counterintuitively, actually, they aren't gravitationally bound, okay, at least not sort of when we see them in this state. So they will disperse over time. So there's not actually enough gravity in the mass of the stars that make it up to keep the cluster together. So you might be wondering why there's a cluster at all then, because how did they get there if they're not gravitationally bound together? Well, the answer comes back to how they formed in the first place. So when there was a cloud of gas that was all collapsing down under its own gravity, then everything was gravitationally bound. But the process of forming new stars is actually quite inefficient. So probably only 10% of the mass of that big cloud of gas that was collapsing under its gravity ended up in the stars. The rest of it, 90% of it, probably gets blown back out again into space during the sort of violent star formation processes. So therefore, even though it was bound when it was forming because of all the gas there, once that gas disappears, then it's not bound anymore. And over time, the stars in an open cluster will gradually drift apart, especially as it sort of orbits around the galaxy. Things will get sheared out and stars will drift off, and it won't stay forever. So we only really see them, soon after they're formed. So they're sort of, again, they're naturally young. We haven't really talked about galaxies or anything yet, but again, we can't do everything in exactly the right order in this module. So for future reference, then these clusters are typically located in the sort of spiral arms of spiral galaxies, like our own Milky Way. So through the disk of a spiral galaxy. We'll come back to that later in the module. And the key point here then is that, as we shall see from the evidence of the color magnitude diagrams in a second, is that open clusters are made up of mainly young, very hot, and blue main sequence stars. Okay. So how do we know this? Well, we plot a color magnitude diagram. Okay. Let's have a look at a couple more pictures first. So here's another nice picture of one. Okay. So this is a color picture. So you can see that most of the stars here are blue, okay, in this sort of reasonably true color picture. Got the odd red one here, and maybe over here, but you can see that most of them are blue. Okay. Another thing you can see in a cluster, which I mentioned before for the general sort of population of stars, is that there's one or two bright ones, quite a few more medium bright ones, and then you can probably see here in the middle a lot more fainter ones. Okay, so this is exactly the same as I talked about for main sequence stars in general. There's a few sort of massive bright ones, more medium ones, and a lot more lower mass ones. Okay. And they will all be present in this cluster. And here's another picture. This is a ground-based picture of a very famous object. So this is actually quite big on the sky. It's a couple of degrees across at least, I think. Actually, maybe not actually, half a degree across. So this is the Pleiades, or Seven Sisters as they're sometimes called. So there are 7 bright sort of naked eye stars here. So you can see this object with the naked eye. This time of year you can see it actually, if you know what you're looking for. It looks a bit like a misty patch, but it's actually made up of these stars. With the naked eye you would not see this, what I would call nebulosity here. Again, this is evidence that there is still some gas and dust left over from the formation of this cluster, still hanging around, hasn't all been blown away yet. Okay, and so this is a very nice example of an open cluster. And here you can see all the stars are still blue. So let's focus on that cluster for a moment, and now look at the first example of our color magnitude diagram. Okay, so what we're plotting here, this is the apparent magnitude. So this is normally designated as capital V in these clusters, in these color magnitude diagrams, against the color B minus V. Okay. And remember that B minus V, as you go to more and more positive values, means that the star is redder. Okay. And for more negative values, the star is bluer. So this still represents a temperature sequence. Okay, so the red ones will be cool, the blue ones will be hot. Okay. And each dot on here would represent one of the stars in the Pleiades cluster. Okay. And you can see that straight away there is this sort of mainly diagonal structure that goes from the top left down towards the bottom right. Okay. And that is exactly the same as the main sequence that I talked about when we were talking about HR diagrams. Okay. So the ones up here will be very hot, very luminous. Okay. The ones down here will be cooler and less luminous. The ones at the top left will be the higher mass stars, and down here will be the lower mass stars. Okay. And this is apparent magnitude here, so in fact these data points up here are the 7 sisters. Okay, these are the bright naked eye stars. So So you can see that they're all like 4th magnitude or so easily visible with the naked eye. As you go further down, there are more and more fainter ones. Again, that's that same pattern that I talked about before. There are more lower mass main sequence stars around than there are higher mass ones. These are quite rare, so there's just a few of them in the cluster. And you can see nothing else on this diagram. There are no red giants at all. Okay, certainly no white dwarfs. Nothing has actually evolved off the main sequence here yet. Okay. So this is telling us that the cluster is also made up of very young stars, because even the most massive star here, so remember that the main sequence lifetime increases dramatically as we go to lower and lower masses. Okay. So even the most massive star, the brightest one here on the main sequence, has not burnt all its hydrogen yet. So that allows us to put sort of an upper limit, if you like, on the age of this cluster, because whatever the main sequence lifetime of that star is, then the cluster must be younger than that, because it hasn't gone over here to be a red giant yet, or a supergiant even. Okay, so you can begin to see that the color magnitude diagram, because all the stars in the Pleiades cluster are all pretty much at the same distance, then 2% on here is not going to be either here nor there. Then you get this beautiful pattern of the main sequence straight away. So that's open clusters. Now let's switch to globular clusters. So these are quite different beasts, really, and sort of amazing objects in their own right. These have many, many more members, many more stars making up the cluster. So easily 100,000. Some of them, the bigger ones, even have up to 1 million stars in them. And these are very tightly gravitationally bound. Okay? So they've been around a long time. The stars aren't leaving because they're bound in by the gravity of the cluster. And again, for future reference, they're not found in the disk of our galaxy. They're actually found up and around in the halo of our galaxy. But we'll come back to that later in the module when we talk about galaxies. Again, the key point here is that the type of stars that you find in a globular cluster are very, very different. They're the opposite of what you find in the open clusters. So they're all old. There are no young stars at all, which means that they're all at the cool end of the temperature range and red. Okay. And again, we will see that from the color magnitude diagram in a moment. So let's have a look at a picture of some globular clusters. So here is a beautiful one. Again, this is taken with the Hubble Space Telescope. And you can see incredible concentration of stars here. So even with the high spatial resolution of the Hubble, you can't even see through the middle here because there's so many stars in the way. Okay. And so you've got this, it's very spherical concentration because gravity is pulling everything and keeping everything bound. Okay, so the stars will basically just orbit around the center of mass of the cluster here. Okay, and they can't fly off and leave. So that's why these clusters have been around for billions and billions of years, basically. And again, this is a fairly true color picture here. So basically all the stars in here, you can see, certainly all the bright ones are red, okay, like these ones here. Okay. And just the general color of the whole cluster is quite on the red side. Okay, so that's a very typical globular cluster. Again, you can see some of these objects with sort of binoculars if you know where you're looking. This is a real zoom in, if you like, with the Hubble Space Telescope to the biggest globular cluster of them all in our galaxy, called Omega Centauri. And here you can just about sort of see through the cluster. You can see the stars in the middle here. But again, all the brighter stars here are basically red stars. Okay. And again, you can see the concentration of stars in the center of this globular cluster. Okay, so let's have a look at a color magnitude diagram for a globular cluster. So here it looks quite different. Okay, so again, we're plotting the same thing. Apparent magnitude V against B minus V. Okay. But whereas before, where we had the open cluster, there would have been a diagonal here where all the main sequence would have been. That's not there. They've all gone. They've all evolved off their main sequence because these clusters are so old. So all you've got left is a little bit of the main sequence here. Okay, so this is all that's left really of the main sequence. So these would just be low mass stars that are still burning their hydrogen. Okay, so stars probably lower mass than the sun, probably, or around about there. And instead, the light is dominated by these stars over here, which are very red. Okay, and you can, again, so these are actually occupying the red giant part of the HR diagram. Okay. So all the really bright objects are red giants in these clusters. And even these stars down here are still pretty red if you compare them. So hot stars would be over here at 0, like Vega, but these are all pretty red. So the sun is at, which is yellow, is sort of 0.6 over here. Okay. So there are no really blue stars in here. Ignore these for now. That's and these ones. That's something to come back to in the level 2 module on stellar structure. So basically, all you need to worry about for this module is that the Fibonacci diagrams for an old globular cluster like this will be dominated by the light of the red giants and what's left of the main sequence. Okay. And we will come back to these diagrams in workshop 3. So workshop 3, you will be using the kind of information encapsulated in these diagrams to actually work out the age of these clusters yourself, so that you can see how this actually works. So these are really very useful. These Fibonacci diagrams basically act like clocks on the stellar clusters, so that you can estimate the age. In fact, you can do it very accurately, work out the age of the cluster. And remember, this is all linked back to this idea that all of these stars formed at the same time. So all of their evolutionary clocks started ticking at the same time. So basically you can think of the main sequence that would have been here. It's just over time, it's just burning its way down through there. So as you go to lower and lower mass stars, as time goes on, they start to evolve off the main sequence. Okay. But we'll look at that in more detail in workshop 3, where you can have a go at that yourself. Okay, so these globular clusters are pretty spectacular objects, as you've just seen. They are, in fact, the sort of they have the highest concentration of stars in space, if you know what I mean. And so that's what I'd like you to sort of have a little think about here, is to estimate the average separation. Again, just keep everything in parsecs of stars in a typical globular cluster. Okay. So I've just mentioned that globular clusters might have something like 100,000 members, so 10 to the 5 stars, and they're all packed into a cluster that just has a radius of 10 parsecs. Okay. So have a little think about that. Can you work out a number that would represent a typical separation, the average separation of stars in there, assuming they were uniformly distributed in that volume? Okay. So as a hint, first, good idea to calculate the number of stars per cubic parsec. Okay. And then if you think about this number, okay, and the dimensions here, and think about packing stars into a volume to make up that cluster, how would you work out the average spacing between them? So if you think about the dimensions of this, you know the kind of mathematical operation that you would need to do in order to turn it into a length in parsecs, because you'll have stars per cubic parsec. Okay, let's have a think about that.